Hi, everybody. Welcome back to the Rule Your Pool podcast. This is episode 142. I'm your host, Eric Knight with Orenda and Hasa, and fair warning, this one is going to be pretty dense. And another fair warning, I got a lot of noise going on. The cicadas are still wild. If you listen to episode 141, I recorded outside. If you can hear them, I'm inside with the windows closed, and it's still really, really loud. These cicadas are nuts. Hopefully you're not hearing them, but I certainly am, even through the headphones. In this episode, we are going to explain how alkalinity works. One of the main questions we get is about alkalinity, various versions of that question. But what people are really trying to figure out is, what does it do? Like, why does alkalinity do what it does? This episode, we're going to talk about pH buffering. Specifically, they're called pH buffering systems because it's not just total alkalinity that does this. We're going to talk about things like acids and conjugate bases, and something called a pKa value. There's also a pKb value, and that's really advanced chemistry. We're just going to touch on it, but there is an article in our blog that we just released that goes in depth on this. Now, before going into this, I don't expect you to understand all of this. It would really help if you could see it and take the time to read the article. There's some graphics in there and some explanations. You do not have to understand every aspect of this episode to be successful in ruling your pool. I just want to get this information out there because it is a building block towards future lessons that we want to teach. And on this journey together that we're doing in this Rule Your Pool podcast, we have to have some fundamental lessons done early on. I go back to a previous episode about molar weights and chemical product percentages. And the feedback I got from most pool pros was, what? Hey, respect. I understand it's dense, but there's a reason I'm teaching this. It's not necessarily because you have to know all of it. It's because it is fundamental to what is to come. And as we get better together, as we continue to learn, I'm right there with you. I am learning as we go. I recently just learned a lot of this. I mean, I knew some of it, but I didn't know all of it. I didn't know why alkalinity does what it does. And now I do. And that's what I'm going to try to share with you today. For the chemists listening, and I know there are several of you because you reach out to me on the email podcast@orendatech.com. We appreciate your feedback. I am doing my best on this, not only to explain it accurately, but to simplify it so people can understand it. Because if I start talking full-on chemistry to this, no one's going to understand it, including me. So I've done a lot of homework to try to distill what this means. All right, so please wish me luck. I hope I get through this. And if you are driving, you might want to change the channels so you don't fall asleep. Catherine, let's get into it. Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go. Let's start with this concept of pH buffering. Now, buffering in this context is a little bit different than what you might be used to if you're frustrated with Netflix because the streaming TV show you're watching doesn't load and you throw your remote control across the room and you yell at your family. No, just me? Okay, never mind. So buffering in this capacity is friction, or its resistance to a change in pH when an acid or a base is added. And when I say acid or a base, let's just replace that with when anything is added to the pool. A chemical, people, whatever. When things get into the pool, they almost all impact the pH in some way. Some of them are negligible. Some of them are major, like acid or soda ash. What do those impacts do? Because it's important, pH itself impacts almost everything else. It impacts the LSI, it impacts disinfection, it impacts how well chlorine can stay connected to cyanuric acid. Even though in a stabilized pool, the pH has what I would consider a negligible impact on disinfection, it still matters for various other reasons. So we're not in the business of telling you pH doesn't matter at all. No. What we're saying is you can't control it. That's a fact. Mankind cannot control pH, but you can use physics to your advantage to contain it. And buffering systems are one of the ways to do this. Alkalinity, as we know it in swimming pools, is primarily a buffer against a reduction in pH. Now, it technically does buffer against a rise slightly, but Usually, because of where our pH is in swimming pools, let's say realistically 7.2 to 8.2 is going to encapsulate most pools. Because of that pH range that we're typically dealing with swimming pools, total alkalinity's value as a buffering agent is lower on the pH scale than that. So it's really buffering against a reduction in pH, not so much a rise in pH. But on the other hand, you could have borate in your water. Not that we recommend you use borate, but I know a lot of people have success with it. Not knocking the practice as long as you don't overdose it. Borate will buffer against a rise in pH. And I've said it in a few episodes before, I don't remember which ones, but alkalinity as we know it is primarily going to be carbonate alkalinity and cyanurate alkalinity. Those are two different equilibriums. They have different buffering capabilities, but they both together yield total alkalinity, which means when you're trying to calculate the LSI and you need to know your carbonate alkalinity, some people call this the corrected alkalinity. I think we should do another episode on this by itself. You have to deduct things like borate and cyanurate alkalinity from the total so that we can, through process of elimination, find out what our bicarbonate and carbonate equilibrium is. We need to get just those carbonates because that's what matters to the LSI. If you're unfamiliar with anything I'm saying, you might as well change the episode now because the understanding that there is carbonate and cyanurate alkalinity is pretty pivotal to what we're about to go into. You might want to go back to previous episodes if you haven't, or read the blog so you can see the graphics. Otherwise, this is going to go over everybody's head, and I don't want to put you to sleep. So let's get back to this concept of buffering. pH is based on water. There is no pH of a dry chemical until it is dissolved in water. This process is called hydrolysis. Thank you, Terry Arco. You're improving my vocabulary every week. Hydrolysis is the technical term for dissolving. It's a chemical reaction in which a compound is split while incorporating a water molecule. All right, that's the technical way to look at it. And so you take an H2O and it may divide up something like salt. So you got sodium chloride, and then you will have sodium in its aqueous form, and you will have chloride in its aqueous form, and that's dissolved. And if you split a water molecule, an H2O, imagine you got Mickey Mouse, the oxygen is the face, and the two hydrogens are the ears. One hydrogen leaves, that's the acid, that's an H plus proton or hydrogen ion. And then the hydroxide is the OH minus, that's like Mickey Mouse Van Gogh. He's missing an ear. That's the hydroxide. That's the base. So it depends on which one of these binds to that compound in water. The more concentration of hydrogens, the more acidic a substance is. So when we add something like hydrochloric acid, more commonly known as muriatic acid, you're adding a very high concentration of hydrogens into the water. But where do they go? That's where a pH buffering system comes into place. If I just put hydrogen into the water, okay, what does it actually do? Well, in a pool that has carbon and alkalinity in it, which should be every single pool that we deal with, when you put an acid in there, when you introduce hydrogens into a pool like that, they are going to be neutralized by the buffering system. That buffering system primarily is going to be bicarbonate alkalinity. Bicarbonate alkalinity is HCO3 with a minus, a negative valence. It's got an electron on there. HCO3 minus binds perfectly with H plus. They create H2CO3 called carbonic acid. If you want to see what I'm talking about, pull over your car or wherever you are, look at the Orenda app, go to the top left, show secondary readings, and tap on carbonate alkalinity. It's underlined, so it's got a pop-up. And you're going to see a graphic there. The red line is carbonic acid, H2CO3. The green line is bicarbonate, HCO3 minus. And notice those are in equilibrium. If I am in swimming pool range, almost everything that I have in my water is going to be bicarbonate. And I introduce an acid, it's going to react with that buffering system, and it's going to convert that alkalinity into carbonic acid, which is no longer alkalinity. Alkalinity is something that can take or give away a hydrogen ion. That's basically what it is. It can receive an acid and it can give it away. But if I already am maxed out, there's no more room for another hydrogen, it's no longer considered alkalinity. So carbonic acid, while it is in equilibrium with bicarbonate, is not technically part of alkalinity. Here's what that means in English. Let's just take a step back. When you add acid to a pool, you'll notice that, of course, the pH goes down, but the alkalinity also goes down. And the reason the alkalinity goes down is because of this. The acid converted bicarbonate ions into carbonic acid. Carbonic acid is dissolved carbon dioxide. H2O plus CO2 is H2CO3, which is the same thing as adding a hydrogen to bicarbonate, which would be hydrogen, H plus HCO3 minus. That creates H2CO3 as well. So it goes both ways. You have this equilibrium. I add acid, I burn through alkalinity kind of, and I convert it into dissolved CO2, which means Henry's Law wakes up and says, hey, we got extra carbonation in this water. We got to lose some of this CO2 so that we can equalize between the air and the water. And so the pH goes up. Because of this alkalinity buffering system, we have carbonated water. Carbonated water, just like carbonated beer or carbonated seltzer or carbonated soda, has to go flat at some point. So it's going to lose and off-gas some of that CO2, which reduces the amount of dissolved CO2, and therefore the pH will naturally rise. It will rise up to the point that we have in our calculator called the pH ceiling. That is quantifiable because if we know the carbonate alkalinity, we know how carbonated our water was to begin with. And if we know the water temperature, we can also tell the exact moment that our quote-unquote beer will go flat. We know when our pool is going to go flat. And if our pool is flat, we can't lose more CO2, and therefore the pH cannot rise any higher. Hence the term pH ceiling. It's physics. It works pretty well. Alkalinity buffers pH because it can take or give away a hydrogen ion. That's a very important thing. If I get my pH up to 8.3, the opposite reaction happens. Instead of taking on a hydrogen, like we're going down in pH, that bicarbonate now gives away that hydrogen, and it becomes carbonate ions. This is why we say you don't want to go over 8.3 pH. If you do, bicarbonate ions shed that hydrogen, and they become carbonate, CO3 minus minus, which happens to match up really well with a cation called calcium, Ca++. Ca++ meets up with CO3 minus minus, and you get calcium carbonate, CaCO3. That is what we call scale, carbonate clouding. All these things are a high LSI violation as signified by a purple number in the Orenda app. So if you ever see purple numbers, even if it's not the LSI at the bottom, if you see purple numbers, that's us telling you, hey, this value is likely to lead to a purple LSI. You probably shouldn't have it. Conversely, if you see red numbers, that's a red alert. You don't want these numbers. That's us subtly guiding you to try to keep your water more balanced and to help you rule your pool. That's why we did it. And you don't have to listen to us, but it's not in our best interest for you to screw up your pools. So we'll put it that way. Now, if you have water with high alkalinity, you have a high buffering capacity. You can neutralize more acids, which means you have more resistance to a reduction in pH. And conversely, water with low buffering capacity or low total alkalinity is more susceptible to larger pH swings. So if I have the same amount of acid, let's say it's 1 quart in 20,000 gallons, if I've got 120 alkalinity, I'm going to make an impact on pH with that quart. But if I cut that alkalinity in half, I double the pH impact of that quart because I have half the buffering capacity to stop it. So I can make a much bigger change in pH with less. Now that sounds like a bad thing until you realize that you get to pick how much acid you put in your pools. You know that, right? So why would we have too much alkalinity in our pool? Why would we over buffer our pools if it costs more money to do the same thing? See, the real problem with having low alkalinity is when people don't measure, dilute, and pour acid correctly. If you're just pouring acid in the pool and it goes straight to the bottom and there's very little buffering capacity and you're not measuring it and you're treating it like it has 120 alkalinity even though it has 70 or 60, yeah, you're going to have a problem because you're going to overcorrect the pH because you have half the buffering capacity at 60 alkalinity that you did at 120. That's where the problem is. It's when habits overcome logic. We should be measuring alkalinity every single week. We should be measuring our acid every single week and using it responsibly, diluting it in a bucket to reduce its density. You may have seen in episode 138 on YouTube what acid does with food coloring. It goes straight to the bottom. So we want to dilute that acid appropriately. But enough about that. I think that's something that most pool pros are understanding now, which is great. Column pouring, it's a bad idea. It's a myth. Always dilute your acid. So let's get further into this and let's talk about how a buffering system works. A buffering system being an equilibrium between an acid and its conjugate base. Whew. You ready for this? Okay. An acid is going to be in equilibrium based on the pH with something that mirrors it based on a hydrogen ion. In the case of carbonate alkalinity, carbonic acid is in equilibrium with bicarbonate ions. If a bicarbonate ion gains a hydrogen, it becomes carbonic acid. If a carbonic acid loses a hydrogen, it becomes bicarbonate. If you look at that chart on the app that I had you pull over for earlier and you tap the underlined carbonate alkalinity, you'll see that graphic. And you'll notice that those lines intersect at 50-50. There's always going to be an equilibrium, meaning they're always going to add up to 100%. You'll have 70-30, 60-40, 50-50. You'll never have 54-50 because that doesn't add up to 100. It's going to be in perfect equilibrium because it's about a hydrogen transferring between the two of them. Hence the buffering. Either it takes a hydrogen or it gives it away. They are in equilibrium. Carbonic acid is the acid, and bicarbonate ion is its conjugate base. Conversely, with borate, you have boric acid, and its conjugate base is borate ion. And cyanuric acid is the acid, and cyanurate ion is its conjugate base. A similar thing, even though it doesn't buffer pH, would be chlorine without stabilizer in the pool. You're all familiar with how the pH controls the strength of chlorine in a non-stabilized pool, right? The lower the pH, the higher the concentration of HOCl, hypochlorous acid, the killing form of chlorine. And as the pH rises, that H starts to jump away. And its conjugate base is hypochlorite ion, OCl-, the weak form of chlorine. So the acid is the active chlorine, hypochlorous acid, and they intersect at a place 7.54 pH, but most people just say 7.5. 7.54 pH, they are at 50-50. And as that pH rises, more of the conjugate base becomes present because the hydrogen is jumping away. So as a refresher, an acid and a conjugate base are in equilibrium with each other based on a hydrogen ion. In fact, all acids have a conjugate base. Now, with any of these pairs, any of these acid and conjugate base pairs, there's going to be an intersection point at 50-50. Like I just said with HOCl, that's 7.54. With carbonic acid and bicarbonate ions, which is carbonate alkalinity, that value is 6.14. And if you're still looking at that alkalinity chart, you'll see a dashed line at 6.14. And that dashed line at the bottom says pKa, and the A is subscript. pKa equals 6.14. So what the heck is a pKa? So if you thought this episode was complicated so far, just buckle up. We're going to get through this together. A pKa value represents the pH in which a concentration of an acid and its conjugate base are equal. Basically, it's the intersection point. It's the 50-50 of the acid and its conjugate base. This happens to be where this buffering system has the strongest buffering capability. Let's use carbonate alkalinity as an example. The closer your pH gets to 6.14, which is the pKa value for bicarbonate, the more resistance it's going to face until you pass it. So if you slam acid and you get past that 6.14, okay, all bets are off. But on the way to 6.14, you have a lot more and more and more and more and more resistance all the way until you get to that pKa value. The same could be said for borate. Borate has a pKa value of about 9.2. And that's resisting against a rise in pH because that pKa value is above where we are in swimming pools. we also have cyanurate alkalinity, which has a pKa value of about 6.9, which is even closer to where we are. So technically, even though we don't have nearly as much, cyanurate is a pretty darn good buffer. We are closer to its pKa value, which means it's buffering quite a bit. Everything that I'm mentioning in this, by the way, is factored into the Orenda calculator. You will notice as you change your CYA level that your acid dose changes. It's crazy. It actually changes because its pKa value is closer to where you are. The more CYA you have, the more acid it takes to do the same pH correction. Now, it might be subtle, but it's in there because we want precision. Most of the alkalinity we have, as I said, is going to be bicarbonate. But stabilized pools, CYA impacts way more than just the LSI and chlorination and killing speed and all that. It also impacts your acid dosing because it buffers against a reduction in pH, which is weird because it's cyanuric acid. But cyanuric acid dissociates into a conjugate base called cyanurate ion. So let's break down pKa. What does pKa mean? I don't know how they came up with these letters, honestly, but P means a negative logarithm. All right, just kind of like pH, the P is a negative logarithm. K is a capital K, means a constant, an equilibrium constant. And the subscript A means acid dissociation. So it's a negative logarithm of the acid dissociation constant. Everybody got all that? Good. In other words, the Ka value is the degree in which an acid dissociates into its ions in water. I'm reading here, by the way. It is a quantifiable measure of the strength of an acid in solution. And thankfully, these values are already known, just like molar weights and ratios. The pKa tells us the optimal pH for an acid and its conjugate base to buffer against pH change. And it also tells us the strength of an acid. The lower the pKa, the stronger the acid and the weaker the base. The higher the pKa, the weaker the acid and the stronger the base. Conversely, there's also the pKb, although pKb is hardly ever used. The pKb is the negative logarithm of the dissociation constant for a base. But again, we don't really use this. It tells us the strength of a base. And you can actually use pKa to calculate the pKb. It's just based on subtracting from 14. pKa values, do you need to remember them? Absolutely not. Just know that if you're trying to do something like a no-drain acid wash or an acid bath or whatever you want to call it, the optimal place to get is to get past that pKa value, under 6.14. If you wanted to do a zero alk startup, which we strongly recommend against, especially in the first 60 days of a startup or so, you'd have to get below 4.3 pH. Then you'd have zero alkalinity. But somewhere between 4.3 and 6.14 is going to be where you should be targeting if you're trying to clean up your plaster surface. Because if you're above 6.14, you're going to face a lot of resistance, and that pH is going to rise back up. So anyway, I hope not all of this went over your heads, because I know a lot of it went over mine, and this took me weeks to actually comprehend. I read a whole bunch of stuff, and I've cited my sources. If I was to summarize it, if you are ever chasing your pH with sodium bicarb, chasing it with acid, you're going through this whole up and down, trying to beat water into submission, it would really help if you understood what you're actually up against. It would help if you understood what a buffering system does, and you might realize you're probably just overdosing acid. You could probably do a lot smaller doses and have less impact on the buffering system itself so that it remains more intact, and your water would stabilize itself quite a bit. Use physics to your advantage. Use the pH ceiling. It's there for you. It's not going away. Physics will never quit on you, even if you want to deny it. It's always going to be there. Use that pH ceiling to your advantage. Keep that LSI balanced, and good luck ruling your pools. As I said at the beginning, this was going to be dense. I don't expect you to understand it all, but it is integral for something that we want to teach down the road. I appreciate all of your time. Thank you for surviving this episode. It was brutal. And by the way, if you're still calling the helpline, we're getting so many calls, it's impossible for us to answer them all. Please do us a favor. Go to ask.orendatech.com, search our help center. Most of the answers that we ever get on the phone are already there. Tell your friends, share this episode, or actually don't share this episode. That'll turn them off of pool care. They'll probably sell their house. Pick a better episode, But you can let people know that this podcast exists. And we hope that you got some value out of this, but I know in the future episodes you will, but we had to get through this first, and I'm sorry. So I love you all. Thank you for your support, and thanks for listening. This has been episode 142 of the Rule Your Pool podcast. Take care.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.